Yes.
Okay, everyone. So greetings on Martin Luther King Jr. Day from California out here. My name is Shankar. I'll be chairing the session of lightning talks. These are talks that are going to be short and sweet. So the 5 minutes each. And, the first presentation will be certified semantics for miniKanren by Dmitry Rosplokas, Andrei Vyatkin, Petro Lozov, Dmitry Purichev. Take it away.
Yeah, I would like to just play my pre-recorded video. I hope you will. Hello, my name is Dmitry Rosplokas, and I will present our project of providing certified formal semantics for miniKanren. miniKanren is a minimalistic embedded language for logic programming with lots of versions for different host languages and lots of extensions for different logical features. Execution in the language is based on a special search strategy called interleaving search. And miniKanren was created specifically for relational programming paradigm, which regards programs as relations. This approach works quite well together with the search strategy, and miniKanren was found applicable to a number of non-trivial problems like proof search and program synthesis. However, these solutions and extensions are usually presented just by implementation in some specific version of miniKanren. And we find this problematic because it can be hard to understand and even harder to reason about. And to do it in a more abstract way, we need some formalism. So our project aims to provide formal semantics for miniKanren suitable for such presentations and to apply the semantics to reason about program execution. We have described an operational semantics for miniKanren that models the interleaving search as a label transition system. The central result we established using it is soundness and completeness of the interleaving search with respect to the denotational semantics. Basically, it means that answers found by the search will cover exactly the mathematical meaning of the program. It had been regarded as common knowledge in the miniKanren community, but actually had never been formally proved before. In addition to this result, we applied semantics to reason about other things like termination and language transformations. Initially, we had focused on the basic version of miniKanren, but later turned our attention to its various extensions for which soundness and completeness of the search are less self-evident. First, we dealt with disequality constraints, the most widely used extension of miniKanren. Here, we added an abstract layer to our semantics and to cover different existing implementations. And we identified a list of 5 conditions on such implementations sufficient for soundness and completeness. Currently, we are working on another extension, a fair conjunction relation strategy, which was presented here at PEPM earlier by my colleague. It was formulated in terms of operational semantics right away, which was necessary to state and justify formally its distinctive property of fairness. All this formal development looks rather fragile when done on paper because our proofs has lots of cases and details, and also because we work with infinite objects. So from the very beginning, we were inclined to support everything with a specification in Coq. And as you might expect, during the mechanization, we found major flaws in our pen and paper proofs. And the parts that seemed obvious turned out to be the most complicated. Now, with the verified specification, we feel more confident, and also we can use the Coq extraction mechanism to extract correct reconstruction interpreters from our proofs. We hope to continue this work and maybe find more applications of our framework. But for now, that's all. Thank you.
Okay, thank you. Any questions?
I guess it's another channel.
Yeah.
Okay, I'll ask one. So can you say something about the parameterization and the modularization you have in the operational semantics? So how easy is it to construct and verify different variants?
Yeah, we are. It depends on the part you're talking about. We have actually some nice parameterization in this extension of these quality constraints I mentioned, and there we can cover many different implementations. But on the basic level, I guess we have less of parameterization. We stick with one variant, which is because there is some canonical implementation of basic search in miniKanren, and we tried to stick with it in the basic variant. But we are working on it. Maybe it's still we are trying to figure out how to what level of parameterization is would be good to apply.
Yeah. Thank you, Dimitri. Yeah.
So Shankar, just to say, since questions have not been scheduled, so maybe we stick to one really quick question for each topic.
Yeah. Okay. Yeah, that's right. Yeah. Just remember, you can always go to the breakout room for the other questions. So the next talk will be Cameleer, a deductive verification tool for OCaml by Mario Pereira and Antonio Rivara. Take it away.
Let me just share my screen. Okay. Okay, I think you can see my screen now. So, hi everyone, my name is Mario Pereira, and I'm here to present our ongoing work on Cameleer, a deductive verification tool for OCaml. This is joint work with Antonio Rivara, also from Nova Links at Nova University of Lisbon, Portugal. If we look at the current state of the art on deductive verification, we can cite a number of different tools that have been successfully applied to the verification of imperative programs. And what is somehow surprising is that deductive verification has been seldom applied to the functional world, with some notable exceptions. Let's think of, for instance, OCaml as an element of the functional family. OCaml has a clear syntax. It features a well-defined execution model, and it is also a multi-paradigm language, so one can write concise, efficient, type-safe code in OCaml. OCaml is also the language of choice to implement what one can call sensible software, for instance, proof assistance, software analyzers, and also blockchains such as the Tezos blockchains. So OCaml code seems like a good target for deductive verification, but yet no usable tool for the deductive verification of programs, of OCaml programs, currently exists. So this is how the Cameleer project enters the scene. Cameleer is a 2-year project funded by a Marie Curie individual fellowship, and our main goal is to build the first automated tool for the deductive verification of OCaml code. One key ingredient of our approach is the use of the recently proposed Gospel, generic OCaml specification language, in order to provide formal behavioral specification to OCaml code. In this talk, I'll briefly describe our first step in this project, which amounts to a translation of OCaml annotated code into the Y3 deductive verification. So what we propose with Cameleer is that instead of using Y3 as of today, which means that you write your code in YML, the programming and specification language of Y3, and then rely on its extraction mechanism in order to get executable OCaml code. What we want, and what Cameleer is doing now, is that it features an automatic translation of OCaml code annotated with Gospel specification directly into YML. So it means that the user, after this translation happens, can still use all the Y3 toolset in order to conduct deductive verification. This is what an OCaml program augmented with Gospel elements looks like. This is a binary search routine, and one can very easily spot specification elements such as loop invariants, variants for determination, but also function contracts, here in the form of preconditions, postconditions, but also exceptional postcondition, and in this case, it is a formula or a property that must hold whenever this function raises the not found exception. So, where are we at the moment? So far, we have been able to build Cameleer as a deductive verification tool usable to tackle the verification of a large subset of the OCaml language, and we have been able to apply it to the verification of several case studies of very different natures. In the future, we would like to prove correct our OCaml to YML translation. Even if OCaml and YML share many syntactic and semantic constructions, we would like to have a proof that we are doing things correctly. And in the meantime, we would like to move to the verification of heap manipulating programs. In a first step, simpler programs by translation into the Viper infrastructure. And in the second step, once we get to the verification of higher order effectful programs, at that point, we'll be building a translation from OCaml annotated with gospel to the CFML tool. I conclude my presentation by providing the link to the GitHub repository of the Cameleer tool, and also a very brief summary of the case studies that we have been able to verify with the Cameleer so far. Thank you very much.
Thanks, Mario. So I think in the interest of time, we'll defer the questions to the breakout rooms and move on to the next talk. So the next talk will be Gradualizing the Calculus of Inductive Constructions by Maveri, Lennon Bertrand, Kenji Maillard, Nicolas Tabarot, and Eric Tanter. So
yes, I'll take resume here. Okay, so good evening, everyone. I'm Lennon Bertrand, and I'll be presenting jointly with Kenji Maillard, Nicolas Tabarot, and Eric Tanter on gradualizing the calculus of inductive constructions. So basically, our work has two main aspects, the gradual aspect and the calculus of inductive construction one. So the calculus of inductive construction is the type theory behind, in particular, Coq, but also other proof assistants like Lean and Agda. I won't be presenting that here. I guess most of you have a good idea of what's happening there. And as for the gradual part, that's what we're bringing there. I'll present it briefly. So the general idea is to have a kind of relaxed typing discipline. To do this, you introduce your new base type, the unknown type, and then using that type, you relax all features of your type system. And in particular, you have a kind of optimistic type comparison that looks like unification compared with equality or conversion in CIC. And to account for this optimistic relaxing, you also add a kind of runtime check to ensure that the assumptions you've made at tapping time are actually valid at runtime. So this incorporates some kind of dynamic typing inside a statically typed language. It's been a research area for now, I think 15 years at least, and there has been a lot of theoretical work on that. Every year of Popple, there are papers on this, and also implementation in more and more programming languages. So I believe it's time to get that also into proof assistance and CIC. And as to why you would want that, the basic aim of gradual typing is to enable easier incremental development. And this is even more pressing when you work with dependent types. So if you've seen this kind of stuff with vectors, when you have index types, you know that this is kind of quite annoying. When you have a filter function that's with index type, then you have to write a complex return type, and then if you want to take the safe head of that, then you must prove that the filter actually computes with a successor, and getting all of this correct right away is quite complex. And so using gradual types there would enable you to have more incremental development, more experimentation before getting your types completely correct. And another point, when you play with CIC and with proof assistance, usually you rely on axioms at some points in your development for things you would want to do later. And those are completely inert. They have no computational behavior. And if you care about computation, which is something important in CIC, then this might disrupt your system. Whereas when using this unknown instead of an axiom, you basically get the same behavior of a wildcard, but then you have a computational behavior. This kind of optimistic type comparison gives you an optimistic handling of the unknown. And then if you've made bad assumptions, then you will still be able to catch those when trying to reduce your terms. So as for what we've done right now, so we have a paper up there with try to have a kind of gentle introduction to gradual types for those who are not really familiar with that, and how and all the kind of problematics that appear when you mix this with CIC. We identify a strong tension between three features that would be desirable in the system. First, the ability to embed all of CIC in a new gradual language, so as to be able to import all kind of existing libraries. Then the normalization properties that is ensured in the context of CIC, that your function are total. And then the so-called gradual guarantees that are properties that were identified in the gradual typing literature as desirable properties of gradual systems. So all three together cannot coexist, but we are still able to design a new type system with basically three variants, each of which relaxes one of the three properties and keeps the two others. And to justify those, we also introduced new models for CIC, which interpret types as order structures. I won't go into further detail, but there's a preprint on arXiv. There's a link on the CPP website on the page of this talk. And we'd be very happy to hear from you either on the breakout room or later on. Yes, thank you.
Thanks, Mervyn. Yeah, I'm sure there are lots of questions. So again, feel free to visit the breakout room. Thank you again. So the next talk will be on formally verified decentralized exchange with Mi-Cho-Coq. Take it away. Yep.
Muted. Still muted.
Do we have a speaker?
Yeah, can you hear me?
Yes. Yeah. Take it away, yeah.
Can you see my slides?
Yes, we can. You want to maximize them?
Okay. Oops, sorry. Is that more maximized? Is it better?
That's good, yeah.
Okay. So I'm here to present this work that I've done with my colleagues at Monadic Labs and also Kristina Sojakova from INRIA. So Tezos is a blockchain with smart contracts. These smart contracts can be used to implement tokens that represent crypto or fiat currencies or other assets. These tokens can then be traded using decentralized exchanges similar to Uniswap on Ethereum. We have used Mi-Cho-Coq, a Coq framework for verifying Tezos smart contracts, to verify the safety critical smart contract Dexter. Dexter is a decentralized token exchange for Tezos blockchain, similar to Uniswap. This has allowed us to remove bugs from the development version of Dexter. Moreover, it has resulted in a detailed informal specification, a formal specification, and a proof that Dexter's final implementation is true to this specification. And as far as we know, this is the first formally verified decentralized token exchange. Decentralized exchanges, such as Dexter, enable token trades without using order books. Instead, Dexter uses a fixed exchange rate that is updated at each trade. Trades are ensured by maintaining a liquidity pool in all tokens traded. Users are incited to lend liquidity to the pool in exchange for a cut of trading fees. Decentralized exchanges like Dexter are critical pieces of software. Dexter currently has a liquidity pool of roughly 0.5 million euros. Combined with the immutability of deployed smart contracts on a blockchain, this is a strong argument for using formal methods to ensure correction before deployment. So the first task throughout this work was to develop an informal specification Dexter in collaboration with the developers at CamelCase. The result of this task was the informal specification. The next task is to translate this into a formal specification in Mi-Cho-Coq. Finally, we write a proof checked by Coq, certifying that the implementation of the contract satisfies this specification. So one thing to note here is that the development, the specification, and the verification stages interact with each other, so that the insights we gain when writing the formal specification translated back to clarifications in the informal specification. During the verification process, we found several issues in the contract. First, we found issues in how parameters are verified by the contract, where the input parameters of the contract would not be verified as we had specified. Second, we found that in some instances, the order in the list of operations that a smart contract can emit at the end of its execution would not match that of the specification. Thirdly, we found instances where the deadline that can be attached to trade orders would be checked by the contract inclusively, where the specification states that they should be checked exclusively. Taken together, none of these issues had security implications.
Can you stay close to the microphone when you speak? You're fading in and out.
Sorry. So taken together, these issues we found, they don't seem to have any security implications to the best of our knowledge. However, these divergences between the specification and the implementation can make integrations with other contracts more difficult. So the Dexter contract is about 2,000 instructions of low-level Microsoft code, and our Coq development is about 3,000 lines of Coq. In total, this work was about 4 person weeks. So Dexter is now live on the Tezos blockchain. So far, this is the largest contract that we've verified with Mi-Cho-Coq. As such, it has allowed us to demonstrate the scalability of our Mi-Cho-Coq framework. However, our formal specification, while it's a higher level logical statement of the desired behavior of Dexter, it does not state all the desired properties of the contract. First, the specification is functional, basically stating a desired input-output relationship for each execution of the contract. We haven't reasoned on temporal lifetime properties of the contract. For instance, we would like to verify that a user that adds liquidity to the contract can always remove it later on. But to do this, we need to improve the Mi-Cho-Coq framework with a finer modeling of the Tezos blockchain. Second, the specification does not state desirable economic properties of Dexter. For instance, it's desirable to show that an exchange satisfies a non-depletion property, ensuring that the exchange cannot be exploited to drain its liquidity pool by a malicious user. So earlier authors have already analyzed the economic principles that underlie constant product markets like Uniswap and Dexter. This analysis has then been carried over to Uniswap and verified in a pen and paper proof. So we would like to continue this line of work by mechanizing this proof in the setting of Dexter. So thanks.
Thanks, Albert. Yeah. Again, now we defer questions to the breakout room. So the next talk will be a semantic domain for privacy-aware smart contracts and interoperable sharded ledgers. Sharon Blake-Kurtz, Andreas Lochweiler, Ognian Maric, Simon Meyer, Phoebe Nichols, Matthias Schmalz, and Ratko Reprik.
Thanks for the intro, Shankar. Yeah, this is joint work with my colleagues from Digital and it's about our approach of reasoning about a smart contract language called DAML. That's an open source language based on Haskell. And one of the core features is it's kind of ledger agnostic. So you can run it on a number of underlying blockchains, distributed ledgers like Fabric, Ethereum, Fisco Beacons, or even just a database. Now, but in order to actually reason about what should be the semantics of this language, what should we achieve, what should we implement there, we've built essentially a mathematical model of what that gives us. And well, a blockchain gives us essentially an ordering service. So a ledger is a list of transactions, not very surprisingly. The interesting bit is that that we've chosen hierarchical transaction because that gives a primitive notion of composability of workflows. It also gives us an idea of defining a privacy-aware projection, meaning, well, some participants to the network may only need to see parts of the data or parts of a transaction, or maybe some transactions need not be shown at all to those, right? The important bit is that this privacy-aware projection should, of course, preserve some notion of causality. And we've also come up with a bunch of notions. What should actually be a valid list of those transactions? So what should be a valid ledger? And we've defined that as the intersection of three properties that you see on the lower right here. There's conformance, so it must obey the code of the smart contract. It should be well authorized, so only those people who are allowed to issue the transaction should be allowed to do so. And authorization needs to play together nicely with composition. And then, of course, there's conflict detection. You don't want to double spend your tokens, your accounts, your money, such that you get there. So we want to reason about these kind of things, but practically, well, main promise of distributed ledgers is essentially to break up data silos, right? But if you run everything on a blockchain, then that blockchain becomes a new data silo, especially if you think about a ledger agnostic system. So you can have a list of transactions abstracted from a Fabric domain, or a Ethereum blockchain, or Fisker or whatever. And then you want to do cross-chain transactions. And if you come up with such a protocol, then of course you end up with only a partial order. So the semantic domain is not really as any more a list, but it's more a partially ordered thing. And you have then a synchronization protocol. In our case, that's Canton, that would synchronize the state across the ledgers. That protocol uses vector clocks to essentially keep track of the causality. And then, well, we want to essentially prove two things. First of all, vector clocks actually are enough to ensure the causality that we need, even if not all those synchronization edges are visible to all participants because we're privacy aware. And of course, we may have a number of Byzantine participants in the system, and we want to be resilient to them. And yet at the same time, well, the vector clock that doesn't advance anything is trivially correct. No, we want to avoid deadlocks. So even if people misbehave, we want to be on the safe side there. Okay. Well, so the current status of our formal verification part is, well, we've formalized in Isabelle the concepts of totally ordered ledger, of hierarchical transactions, authorizations, double spends, whatnots, and essentially proved that all these concepts play nicely with the privacy-aware projection to individual participants. What we're currently working on is relaxing this total order to partial orders and implementing the vector clock stuff. And something that is still very open, and if you have nice ideas how to capture that, is essentially how to define a notion of deadlock that works without ruling out too much. If you want to find a bit more information, the language itself is described on daml.com, and the protocol for synchronizing across different ledgers is Canton on canton.io. Tomorrow evening, there will be a sponsors event, because Digital Asset is one of the sponsors of CPP. At 8 p.m. in the breakout room for Digital Asset, you will find a Zoom link there, where you can find a bit more information on DAML and Canton and these background concepts that we're developing. Or just stick around in the breakout room. I'm happy to answer any question you might have. Thank you.
Thank you, Andreas. Okay, so the next talk will be the specification and model checking of Tendermint consensus in TLA Plus by Igor Konov, Zako Milosevic, and Joseph Widow.
Hi, thank you. Just make it full screen. Do you see the whole screen?
Yeah.
Perfect. So, thank you. So my name is Igor Konov. I'm working now at Informal Systems, and that's a short talk about the work we have done together with Žarko Milošević and Josef Fieder. So just to say a few words about Tendermint. That's a consensus protocol that follows the classical approach of DLS, Dvork, Stockmeyer, and PBFT. It works under partial synchrony, and it implements Byzantine fault-tolerant state machine replication. You can follow this archive paper that you see there and see the pseudocode of this algorithm. You can see also the POTSI-like formal reasoning about why this algorithm is correct. But it's a mathematical reason, not a formal verification reason, right? So it's an efficient consensus algorithm. It's open source, and it powers several blockchains, including the Cosmos infrastructure. So what is particularly interesting for us in Tendermint, there are two properties. The first one is safety. So when we have less than 1/3 participants faulty, if less than 1/3 of participants is Byzantine, then we should prove that actually it should be not possible to create a fork on the blockchain. So we should be able to prove that there is no disagreement about the values that different participants voted on. But say it might happen that you just have one more fault, and then you have more than 1/3 process is faulty, or just 1/3 process is faulty. What do you do in this case? In this case, what we want to show accountability, which means that you might have a fork. It means that one part of the system has voted on one value and another part of the system has voted on another value. You might have two different blocks that the participants voted on. What's important here, you should be able to generate an evidence and show that, say, f+1 participants actually misbehaved. That's what we call accountability. And there are several scenarios of how processes can misbehave, and we want to show that in a model checker that this kind of misbehavior possible, and that's the only kind of misbehavior that we see in this case. So what we did here, we didn't do any theorem proofs. We specified Tendermint with safety in mind and accountability in mind. We specified it in CLA+. It's a rather small specification, about 500 lines of code. We wrote an inductive invariant in CLA+, also about 400 lines of code. What's important for us here is that engineers can follow these specifications and understand it. Probably they cannot write it, but they can follow it. And then what we did, we checked these properties like safety and accountability with a symbolic model checker that we are developing. That's the Apalache model checker. We checked agreement, accountability, and the inductive invariant that we have constructed. Unfortunately, we could do it only for small parameters, like for 4 processes, 7 processes, and a small number of faults. So that's the problem with model checkers, even the symbolic ones. What would be great to do, it would be great to prove that this algorithm actually works for arbitrary NNDEF using, say, your theorem provers that you like to use. And as an example, I can tell you that Julian Loza and his colleagues at Galois recently has shown that this algorithm indeed satisfies agreement and accountability for arbitrary parameters, but at a higher level of abstraction, unfortunately. And they did it with Microsoft Ivy. So if you're interested, you can follow this link. And of course, it would be interesting to see how to prove termination. Thanks a lot. You can visit the informal room later, or you can just chat with me in the breakout room. Thank you.
Thanks, Igor. Okay, the next talk will be formalization of combinatorics on Word with Isabelle Hall. So yeah, please go ahead.
Okay, so can you see my slides?
Yes, we can, yeah.
Yeah, okay. So good evening from Prague. My name is Stepan Holub, and I want to advertise here our ongoing project on formalization of combinatorics on words. So by words, we mean just sequences of letters. So this is just the well-known data type of list, which of course has very good, is very well covered in the main library of Isabelle, and we heavily built on this. But our focus is a bit more specific, namely, we are interested in equations on words. So to explain what this means, this is a simple example. So for example, the equation xz equals zy is an equation on 3 words which characterizes conjugate words. So this is equivalent to x and y being conjugate. And so this is a simple example of a formalized proof. But actually, our motivation is much more ambitious than this example would show. So our main motivation is that actually in this field, the open problems are very, very close. They are not far away. So it may be, for example, quite surprising, I think, that this equation, this fairly simple equation, is currently unsolved. So it's an open problem that this equation has a non-trivial solution. So you may say now that formalization is not intended to solve open problems, but actually we kind of believe or hope that in this particular case, it could help. And the reason is that the answer to this kind of questions may be just too complex for a traditional human proof. It's not necessarily so that it requires an ingenious new idea. So for example, this is a snapshot from PhD thesis of my student. And you can see that this case analysis is so tedious that it's very likely to be close to the borderline of what is humanly manageable for the author, but also for the reader, and also importantly for a referee of a paper. So to summarize our project, we are interested in, we are formalizing foundations of combinatorics on words, which includes also creating a textbook for a basic course and suitable for teaching. And then we are formalizing existing in literature proofs, which are hardly readable and therefore often ignored. And finally, we are trying to push boundaries towards open problems. So concerning this third item, actually at the moment we have in print the formalization of this classic result as an example, which is almost 40 years old. And it is quite simple claim that characterizes an intersection of 2 regular languages generated by 2 words. So it's quite elementary result, but it's not widely known. And we believe that this is an example of results that are not known because maybe the proofs are too involved to follow. So thank you for your attention, and you are welcome to and invited to check our existing already formalizations on our GitLab, or you can ask me a question in the break room. So thank you.
Thank you, Stefan. Okay, so the next talk will be Formalizing MPC-in-the-head-based Zero Knowledge by Nikolai Sidorenko, Sabine Oxner, and Bas Spitters.
Yes, great. Hello, everyone. Let me just share my slides. There you go. Can you see them?
Yes.
Great. Okay, so to present our work on formalizing zero-knowledge protocols based on MPC protocols. So for those unfamiliar, in very simplified terms, the zero-knowledge is fixing a function and then showing that we know the preimage of this function for a fixed output without revealing what the preimage actually was. So this has numerous applications, but primarily it's seen in blockchains to preserve privacy. but also it's used as a building block for many other cryptographic protocols. On the other hand, we have MPC, which works similarly by fixing a function, but now we observe the function as a circuit. Now you allow n different participants to give their inputs to this function, and they want to distribute the computation amongst them. At the end, they'll arrive at an output by evaluating each gate in turn. The point of this protocol is that by supplying an input, none of the other parties will get to know what input you supplied. Now, both of these problems in isolation have been looked at and formalized before. But what we noticed is a lot of it has been basic constructions, such as constant round MPC protocols or Schnorr's protocol for zero knowledge, or MPC protocols with a constant amount of participants. Also, most of these protocols that we've seen formalized are taught in master level cryptography courses focused on MPC. Moreover, the MPC formalizations that we've seen usually lack the simulator-based proofs that you see in cryptographic papers. Or if they actually do simulator-based proofs, they only do them for parts of the system and not the entire system. So our work consists of taking a research level zero knowledge protocol called CPP. Now this protocol is interesting because it uses MPC as a sub-procedure. So you run MPC and then use the security notions of MPC to automatically derive zero knowledge. And interestingly, an optimized version of this protocol is an alternate for the NIST candidate for a post-quantum secure signature scheme. Now we take this protocol and fully formalized it in EasyCrypt. And for those of you unfamiliar, EasyCrypt is a proof assistant with a probabilistic relational Hall logic, which also has a lot of automation through SMT solvers. Okay, so to formalize a protocol like this, you face numerous challenges that we have to overcome. So the primary one that we talked about before is the lack of simulator-based proof in these MPC protocols. What we've managed to do is actually derive or show a simulator proof for the entire protocol. So the reason why this is difficult is the way you compute an MPC protocol is that you start from an input and then everyone works from the input towards the output. And this is the same way that you would simulate it. You would start from the input and then you would simulate all the computations toward the output. Now, the problem is that in an MPC protocol, the output is known to everyone. So by simulating it, you would start from the beginning and then you would get to the end, and there would be an additional constraint all of a sudden that the output needs to match this output. So beforehand, most proofs are only focused on doing the gates in isolation, and then they've forgone the latter part by showing that this actually reconstructs for the entire system. Moreover, since this protocol that uses MPC as a sub-procedure, when actually formalizing MPC and zero knowledge in this proof assistant, you need to be careful in the way that they interact, such that you can clearly specify what the properties of MPC is, such that they directly imply zero knowledge as given in the CPP protocol. Managed to solve these problems, and if you're more interested in how these problems were solved, we expect there to be a paper out soon on ePrint where you can read it. Otherwise, ask me in the breakout room.
Thank you, Nikolai. So the next talk will be mechanically checked soundness of type-based null safety by Alexander Kognenko.
Thank you. Software is buggy. One source of these bugs is a problem of null pointer dereferencing. It is caused by the possibility to access a reference that may be null at runtime. Indeed, even in such type-safe languages like C# or Java, it is possible that some variables or expressions in general don't reference any existing objects or are null. If such an expression is used as a target of a qualified call, it leads to an exception. In other words, behind the simple syntax of a qualified method call, there is hidden semantics that ensures that if the target is null, an exception is thrown. This minor discrepancy between syntax and semantics plays a major role in various software vulnerabilities found on local computers and the internet. The first step to avoid this problem is to extend a regular type system with notions of non-null and nullable types. A non-null type is used to specify the type of expressions that always return an existing object. A nullable type is used to specify the type of expressions that may return null. The type system rules specify when a source expression can be assigned to a target variable. In particular, it's not permitted to assign a nullable expression to a non-null variable. However, when a new object is created, all its fields, including those of non-null type, are set to null. Therefore, there should be a mechanism that guarantees null safety for non-completely initialized objects. One such solution was proposed by Alexander Summers and Peter Müller. They suggested extending the type system with so-called free and committed types, where a free type is used for an object that has not completed its initialization, and a committed type is used for a completely initialized object. This adds two more rules to the type system. One covers assignment to object fields, and another one specifies how to compute the type of a field depending on the type of the target object. Using this type system, they prove the following theorem. If a program starts in a good environment, where the state of local variables and the state of the heap satisfies type constraints specified by the program, and the program itself satisfies the typing rules, and the program terminates, then the resulting local variables and objects in the heap are well typed, and the program does not raise a null pointer exception. To ensure that this is indeed the case, I translated the formalization into Isabelle Hall. This slide shows the difference between the original proof on paper and my text in Isabelle Hall. It's just a fraction of all the changes that I applied to complete the proof. The critical part is the proof of all execution invariants, predicates that hold before and after executing an instruction of the model object-oriented language. Its operational semantics includes 11 rules with 6 non-trivial ones. Just multiplying 20 predicates to these 6 cases gives more than 100 of non-trivial goals to prove. I discovered that the original proof mistakenly used at least 2 invariants. Fortunately, I found the required replacement invariants and completed the proof. To my knowledge, this is the first complete mechanically checked formalization of null safety. It means that if the model language can be correctly extended to a real one, developers can forget about null pointer exceptions in their programs. I think the next challenge would be to mechanically prove similar guarantees in Eiffel that does not use any additional type annotations. Let's make software a bit more flawless. Thank you.
Thank you, Alexander. The next talk will be Formalizing MiniSail in Isabelle by Mark Wassel. So Alexander, can you stop sharing?
Just a second.
Okay. So Mark Wassel. We can't hear you.
Yeah, I just needed to unmute. Can you see my slides?
Yes.
Thank you. So I'll be talking about my work to formalize MiniSail in Isabelle. First, a thank you to my supervisors, Peter Searle and Neil Krishnaswamy. First, what is MiniSail? MiniSail is a core calculus for Sail. And as you would have heard earlier today, Sail is a language for specifying instruction set architectures. To make it engineer-friendly, Sail includes imperative features such as mutable variables, while loops, and statement sequencing. Bit vector is an important part of instruction set architectures, and to help track bit vector lengths, Sail has a lightweight dependent type system. This work is motivated by the following. First, CPUs are crucial, so it is important that we have confidence that the language used to model them is correct. Second, I wanted to investigate how language metatheory mechanizations can be used to validate language implementations. Finally, the nominal solution to binding has a nice mathematical feel, and I wanted to explore how this worked. MiniSail is constructed to include key parts of Sail, mainly the imperative features and dependent types. The type system is a refinement type system, where a type is composed of a base type and a refinement constraint. We use A and F so that complex terms are broken down into a nesting of let statements. This makes typing explicit for subterms and simplifies the rules. The type system is a bidirectional one. We have type checking for top-level statements and type inference for expressions and values. The operational semantics is single-step reduction and includes a store for mutable variables. How is the mechanization constructed? Well, I use nominal to Isabelle for the binding, and in this we use nominal data type for the language AST, and this AST includes a specification of the binding structure. From this binding structure, nominal Isabelle constructs the alpha equivalence relation and does the quotienting automatically. In the AST, we define a number of term varieties, values, expressions, and statements. We define substitution classes and instances for the term varieties. The mechanization is split into two tracks, one defining the predicates up to operational semantics, and one with the proofs up to safety. We set up inductive predicates for well-formedness, typing, and the operational semantics. The object of the mechanization is to prove safety, and for this we prove the usual substitution and weakening lemmas, and also, because of the type system, lemmas about the refinement logic. From this, we prove safety via progress and preservation, and for the latter, we need to take into account that we want the store to remain well typed after a reduction step. So my experience doing this work. The high-level structure of the proofs was obvious, and is basically driven by what is needed to prove preservation and progress for each case of the reduction predicate. The challenge is in the detail, particularly where binding is involved. Throughout the development, I've been able to constantly refactor and trim down a lot of the proofs. Once my experience is solidified, and I've worked out useful proof patterns. The type system requires large inductive predicates, often mutually recursive, and care is needed when constructing the Isabelle proof command to set up rule induction correctly. A key lesson I learned is to steer clear of the low-level nominal permutation operator and obtain to get fresh variables, and instead to use the mechanism in nominal Isabelle to get fresh variables that avoid terms. For example, when proving weakening, you can specify that you want any fresh variable to avoid or to be fresh against the larger context. I also use the IceBack proof tool to help automate tedious freshness proofs. This work comprises about 1,000 lemmas and 20,000 lines of Isabelle and took about 9 months. And this will be considerably less for an expert who, if I was to do it again for a similar language. One issue I should point out is that debugging large inductive predicates in Isabelle is quite tricky. One problem being that error messages are not helpful in locating the precise rule clause with the problem. So future work. I've developed an Isabelle specification of a cell type validator. This takes fully type annotated cell AST and validates it. I've also developed a converter from cell to MiniSail, which includes compilation from cell's complex pattern matching to MiniSail's much simpler pattern matching. From the inductive predicates for these, I've generated code and explored plugging this code into the cell implementation. an open question for me is how to generate code from the predicates defined in nominal Isabelle. One option is to define the system using de Bruijn indices, and then to prove a relationship between this system and the nominal one. The Git repo and HTML of the theory files can be found at these URLs. Thank you.
Thanks, Mark. So the next talk will be how to verify an ASN1 protocol C language stack in Coq by Nika Pona and Vadim Zeliva.
Hi everyone. So I will tell you about our project at Digamma AI. Oh, can you see the slides? Okay.
Yes, we can. Yeah.
Okay. So as a full screen. Okay. So I will tell you about the project at Digamma AI. We are verifying a mature open source ASN1 compiler, ASN1C, using the Coq proof assistant. So ASN1 is a language for defining data structures and rules for serialization and deserialization. Initially, we focused on a subset of ASN1 used in the X509 standard, which defines the format for public key certificates. So we're working with C Semantics, and we rely on work previously done by Pomset, which is a verified compiler for C written in Coq and proved to work correctly. So what we do, we parse C code into a Coq abstract syntax tree using C-Lite generator from Pomset. We write specification in Coq, and then we prove that the generated AST behaves according to the specification. And we use semantics of C, which are defined in Pomset. So here is our verification architecture that we came up with. So as you can see, there are several steps. We start from the ASN1 standard, and we have several abstractions levels, and that go back to the C code. So I will explain this verification structure on a simple example of a Boolean type. So we start with the ASN1 standard, which is written in English. So it says things like Boolean value false goes to octet, which is all 0, and true goes to something else. And then we translate this text written in English into Coq. And for each type, we have an inductive type or a relation between an abstract type, which here is just Boolean, and list of bytes, which corresponds to each rule defined in the standard. Also, we have predicates for tags and lengths. So in the end, we have a relation between an abstract type Boolean and tag length and value. And on the bottom of the picture, you saw the C code, and this is an implementation of decoder and encoder according to the ASN1 standard. And what it does, it not only computes the value, but also manages memory. As you can see here, it calls to assign some memory, and then there's some bound checks. And what we need to do is to connect these two levels. How do we do it? We introduce another abstraction level, which we call executable spec, which is a function written in Coq, which abstracts the computation which is done in the C functions that you just saw. So here you can see that it checks tags, checks lengths, and then just writes the byte. And this is what the C function did. Then what we can do, we can prove that this executable spec corresponds to the high-level spec. And we can prove some other properties about this executable spec. And in the end, we connect the C code to this executable spec. So we say that, and we do it in the separation logic using the verified software toolchain. So we say that this function, after executing, it outputs the Boolean decoder, the executable spec Boolean decoder output. Also, we state some memory specifications. So at the beginning, we say that some buffer points to the list of bytes, and in the end, it doesn't change. And for other values, we say that they actually change, and we assign some new memory. So the status of our project is that we finished the proof of concept stage. We verified encoders and decoders and all of the auxiliary functions for them for Boolean in integer types. And we came up with this architecture and tested it. So now we are ready to apply it to the full ASN1C verification. Our project is in active development right now, and it requires significant effort. And the Gamma AI is committed to sponsor the initial stage of this project, and we're looking for industry and academic partners to continue. So please join the breakout room if you have some questions, and write us email if you're interested in joining our project. Thank you very much.
Thank you, Nika. The next talk is Monadic Second-Order Logic in Pomset Languages by Tobias Kappe. Tobias, we can see your slides.
Hello, world. Can you hear me?
Yeah, we can hear you.
All right, excellent. Okay, yeah. So I want to tell you about Monadic Second-Order Logic and Pomset languages. Caveat, I am new to this community, so I'm probably doing things wrong, in which case, please tell me and I'll learn. So I'm interested in verification, and by that I mean that we have a program which has some semantics and a logical formula, and we want to find out whether all of the behavior of this program satisfies the formula. Specifically, the program that I'm looking at has a semantics in terms of these things called pomsets. And you can think of pomsets as partially ordered words. So they have letters and a partial order between them. In this case, there's an event labeled A, followed by two events labeled B concurrently, and finally an event labeled C that follows these two concurrent events. The formulas are given in monadic second-order logic, which means that you can make statements about the events, their labels, their ordering, and sets of events as well. So here I have a formula that says for all events that are labeled with B, there exists an event that is after this first event X, and this event is labeled with C. The pomset on the left satisfies this property because there are two events labeled B, and they are both followed by an event that is labeled with C. The nice thing about formulas like this is that they are comparatively easy to write. They're kind of declarative. What's less nice is that they are hard to compare to these programs. Luckily, there is this very nice theorem due to Buchi, Elhot, and Trachtenbrot, which says that if you have a monadic second-order definable language of words, so not pomsets, but words specifically, then you can construct a finite automaton for that language. And this is nice because you can then compare that finite automaton to the program that you start out with using methods like biosimulation. However, on the level of pomsets, this correspondence is not as nice. There's this theorem by Kuske, which is a beautiful theorem, so not to throw any shade on it, but it's a bit less powerful because it says if you have a language of monadic second-order definable pomsets, then there exists this thing called a finite bimonoid that recognizes that language. Now, what a finite bimonoid is doesn't really matter at this point. You can think of it as an automaton. The important point is that this theorem is not constructive. It tells you a great deal about the structure of the finite bimonoid, but it doesn't tell you how to compute its transitions. So my objective for this project is to give a constructive translation of monadic second-order logic formulas to bimonoids. I want to prove that this translation is valid in a proof assistant, in this case Coq, and I want to be able to extract that code into a language like OCaml or Haskell, and then use that for model checking. So let me just go over some of the types I have. A pomset is a record that consists of a carrier, an order on the inhabitants of that carrier, and a labeling. Formulas, I'm modeling those using a simple inductive type. So you have assertions about orders, membership of sets, labelings, and then you can combine them using disjunction, negation, and existentials. And there's a prop that says, given a formula and a pomset, does the pomset satisfy this formula? What I want to do and what I'm working on is giving a translation from formulas to bimonoids. So I'm taking a formula which has some free variables possibly, and I want to output a bimonoid. And then the final objective is to prove this lemma, which says that given a formula without any free variables, if I translate that formula into a bimonoid, then for every Pomset, if I evaluate that Pomset in the bimonoid that I get from my implementation, I obtain true if and only if that Pomset satisfies the formula that I started out with. Some final thoughts. I think it's nice to implement this in a theorem prover because it forces me, because of the way I set up the types, it forces me to be constructive. I'm still learning, so I'm currently working out how to use finite sets in Coq. That might seem easy to you. It's new to me. If you want to talk about any of this, please shoot me an email. I'm available at this address. That's all. Thank you.
Thank you, Tobias. That's very nice. I don't know if you're doing things correctly or not, but that was just fine. Okay, I think that concludes the session, and we can all escape to the breakout rooms now and start questioning the speakers. I'll hand it over to Catalin and Andre if they have any remarks.
All right, thank you very much, Shankar, and thank you all for the very informative and very efficient talks. So we were really on schedule. So yes, so please let's meet in the Clowder rooms. I understood that there are some people who are having problems accessing Clowder. Are there still such problems, or in the meantime they have been resolved?
Well,
okay,
I have trouble finding my breakout room.
So if you go on,
if I search for breakout or for
sometimes the search, I think it.
Yeah, the breakout room is not necessarily created, but there is definitely a room for your paper.
Right. So this is where we go to the rooms associated to papers. People can go, and if the authors go into their rooms, there will be people there with questions and suggestions, perhaps. Hopefully, in some cases there is the time is quite late, but also people can leave comments in the form of chats and in the form of right. So they can leave comments in the chat. Sorry, and yeah. So communication can continue asynchronously as well at the associated paper.
Yeah, I think this was one of the best sessions of CPP.
Yeah, it was very lively.
Live talks.
And
yeah, the speakers did great. It was very clear. All the talks actually managed to make a lot of sense despite the brevity.
Can you stop the recording?
Talks are really good.
Sorry, Leonard.
Sorry, I was interrupting someone. I was just thinking. Also, I found over the last 2 days, actually, all the 10-minute talks actually really well presented. So I think.
Yeah, Leonard, can you stop the streaming?
Stop streaming on YouTube.